All right, get that going here in a second. Don't need all my email open. All right. And yep, my mic's on. Look at that. We will remember how this all works one of these days. All right. So project 3 did get pushed out till Wednesday because I know a couple people wanted to meet. I talked with a couple people this morning. I'll be around. I've got class after this and then a lab after that. But if you're around in the afternoon, I could probably chat with you while I'm in lab. Usually it's not the busiest time. Other than that, shoot me a message. I can meet up another time. But we'll do that on Wednesday in case we need a little extra time for a little commander project using linked objects, not linked lists. Right? Linked lists was the generic, I can hold any type here as a list in this link structure. This specifically said a particular class will know what instance comes next using pointers and which one comes next, which one comes next. It's just a way of storing data, and we're just practicing it here. So we'll talk about searching and sorting today. On Wednesday, we'll talk about project 3, and we'll talk about the group project. I would love for you folks to do it in pairs. I think you'll have a much better time of it. But that's okay. Not everyone likes to work together, and we're still a global pandemic, slightly more endemic now, but that's okay. And group work wasn't a particular outcome here, so it's not required. Other classes you'll have particular group work assigned. So I like group work, and it's actually kind of lonely. As much as we like to joke about software engineers being the kind of people that like leave me alone, let me just sit off and be quiet and do my own thing and never talk to people. It's not fun to just be alone all the time, and you're not going to get as good of a product out of it, right? The idea that software is an art is really true. There's so much more that goes into writing software than just the science of things. So the design process, collaborating, figuring out what ideas are going to work, trying them out, testing them, debugging is much better with people. So hopefully, I hope for all of you to work on a nice team with really smart people. The one piece of advice that I got from, I forget who it was. I had a bunch of different bosses over the years, but their advice was if you're the smartest person in the room, you should find another room. And that's eventually why I left the one company, because it didn't allow you to grow as well. So try and find people who are smarter than you, work with them, and learn from them. And it's just phenomenal because there are always things to learn here in the field. So it's one of the reasons I like it so much. All right, so searching and sorting here from chapter 14. This is almost our last Zybooks chapter. We'll get into streams, chapter 15, after we get back from Thanksgiving break. So we have, it's nice we have the whole week off, I guess. Makes the schedule easy. But I don't feel so bad having you do group project work like the Monday, Tuesday. I guess some people travel. So if you're traveling, I apologize. But I was kind of counting some of that into your work time for the group project because it's about a month, right? If we're going to start on the 16th, have it due on the 12th, about a month. And our Monday, Wednesdays, like you're probably not missing a whole lot for Thanksgiving. It's not like we're a Thursday class where you're going to be busy all Thursday. So I'll have some time to work on that. So streams, working with files, we'll spend all of Monday on. Ethics is a relatively quick chat here. Super important topic. I don't mean to do it short service or anything, but it's not like a big collaborative exercise or anything. And then your lab that week, you'll do a little ethics scenario and then a little write-up on it. So not a coding lab, which is it's different, but it's really interesting. And then having a chance to talk intelligibly about ethics is really important. And we'll get there. We'll talk all about this. So you don't want to become one of those places that gets in the news for having terrible software practices that do bad things and cheat people out of money or lie to people or be Theranos and lie that your product does these sorts of things because it has amazing software and hardware and then it doesn't do it and then you're found fraud. It's a bad place to be. So talking about ethics is good for sure. And then what do you do as a software engineer when someone asks you to do something unethical? We can point to some things that just gives you some legs to stand on, which is really cool. And then the last week, I have no plans for new stuff. So the plans is I'll show up, I can work with you, work with your teams, work with your groups. If you have questions, again, float around. Just open work time for you folks to get together. Again, if you're working in pairs, you're probably both already here. Although, the size of the class and the people who show up, that's okay. I want it to be a flexible format. Work remotely with your partner. We've got lots of good tools here. Hector, my friend, thank you so much for donating to the Student Scholarship Fund here at the University of Michigan Dearborn College of Engineering and Computer Science. They sent out a new fast facts and figures. Do you guys ever get those fast facts and figures? It's super interesting here. We're not having. So in 2022 here, the College of Engineering and Computer Science here, enrollment by college, we're actually the largest college now on campus. If you flip back, I was looking at this for some reason at some meeting here. This was 2020 enrollment by college. College of Engineering and Computer Science was smaller than Castle in 2020. So in just those 2 short years, and that was up 118% since 2009. I'm really bad at percentages, but 100% growth is doubling, right? So this would have been like around 1,000 in 2009.
I thought it was 200%.
What's 100% increase?
That's just it stays.
An increase. This is why I'm bad at, like, sometimes numbers are hard for people. Like, I don't know, communicating numbers can be difficult sometimes. So we're now officially the largest college on campus here. I think it's interesting. Other people, especially my union, have other feelings about higher education and STEM degrees and things, and that's okay. It's. I'm sorry.
Union?
Yeah.
So do software engineers usually have unions, or is this just?
This is the lecturers' employee organization here at U of M. So there's tenure track faculty and there's non-tenure track faculty. So that's why I'm a lecturer. I can't use the title professor because the university doesn't allow me to do that. That sort of thing. So the lecturers union, we have discussions and all sorts of things. So like U of M Flint has been in the news. They're not doing very well. They're going through a restructuring, re-envisioning process and all sorts of fun stuff here. And it seems to be the writing on the walls is they'll become a STEM school only. We'll see what comes out of their plan, but they're going to have a year's worth of meetings to determine this thing that everyone knows what they're going to do already. And I just don't understand sometimes, but that's okay. So we'll see. But so College of Engineering and Computer Science seems to be doing well here at Dearborn. Yeah. It's all off topic. It's okay.
Do software engineers have unions, or is that very rare?
That's generally pretty rare. Yeah. So unionization in software engineering is not very common that I know of. A lot of it depends on the organization, I suppose, but historically, no. No, most, maybe not even most. Traditionally, union jobs have been like hourly-based jobs, labor-based jobs, and not that software engineering is not a labor or anything, but it's a little harder to quantify software engineering work because it's not. You sit at your desk for 40 hours, you're doing so much amount of time, easy to quantify because it's a creative work. It's hard to do those sorts of things with creative processes, but not impossible, that sort of thing. And that was news going around that maybe Twitter should have done that before. If they had a union, it'd be a little harder to fire half the people there. But that's just a story at this point. So yeah, I don't know how we got here. To donate to the scholarship fund. So yes, so the scholarship fund here for now the largest college on campus. Pretty cool. Thank you, Hector, for being such a friend. That's how we got here. Yeah. So let's start up a new project. Let's do a new project. Oh, and winter registration is open now, right?
Yeah.
Very cool. So take a look at your winter schedules, see how that's going for you. So let's do searching. This is week 12. Just searching and sorting? Okay. And sorting. I'll forget the weeks then. That's easy. All right, so let's add a new source file here. So we looked at some of the built-in searching, right, with finding. When we looked at the STL, standard template library, where we could use find, I told it, hey, find from this beginning point, find to this endpoint, tell me where it is inside the list, right? So that's a basic find. So when you search for something, we talked about the performance of algorithms, right? Let me include our stream. I think that's a little too large for the font, right? Probably return 0. I've been bad about returning 0. Probably should be returning 0 a lot more often, but that's okay. All right, is that still viewable? Not too bad. So when we did find, right, we would start at one point, look at this one, look at this one, look at this one, look at this one, look at this one. So in terms of n items, it's going to take me about how long to find something in a list? Right, the more n I have, is it going to take longer, shorter, the same? Take longer. So in terms of n items, right, it's probably O of n on average. It will probably take me n lookups, n operations to find something in an n size list. And again, if it's, if we want to find the first thing, it's very fast. So the best case, it's the first thing, we're done. Sure, one operation. Worst case, it's the last thing. We had to look at n things. It took n. So best and last aren't all that interesting sometimes. So on average, it's probably somewhere in the middle. Sometimes it might be near the end, sometimes it might be near the beginning. So like half of n would be our good average, but we throw away coefficients because it's made up math land. So still O of n, right? Half of n is still n as far as we care. So a basic linear search, just here's the first one, here's the next one, here's the next one, here's the next one, here's the next one, here in an unsorted list is slow, right? But if we had a sorted list, we can do better. And so that's our first looking at a sort here. And we did this with our number guessing game, right? We call it a binary search. Let's start in the middle. And now if I know if it's less than or greater than, I've cut off half the list. So when we look at the performance of a binary search of a sorted list, it's no longer O of n. We can now be logarithmic of n because we're cutting off half every time. So we're taking half and getting rid of that half, and then this half, and then that half, and chunking it down from half to a quarter to an eighth to a 16th, on and on and on. So anytime you can get that power of 2 in there, start talking about logs, we're in good shape. So we could write our own binary search if we wanted to. Now I think Zybooks, I probably should go and look here. When we talked about recursion and talked about the binary search, didn't it? Was that in Zybooks? Is anybody reading Zybooks? You spent money on it. Doesn't mean you read it. It's okay. I understand. It's what it is. That's why, like in 150, you get points for doing it. But I felt silly trying to give points for doing it here. Right. Okay. Yeah. 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 So we can have a recursive find here that will tell you probably. So if we're going to tell you what index it's at, right? It'll be an integer here. This is a what do you want to call it? Recursive binary search. Now I'm going to use vector because it's easy here. Vector. I don't like dealing with arrays and that sort of thing. That's fine. So we have a vector type int, which is my numbers here. And then on the recursive part, we'll know what our starting point is, what our ending point is. So we'll have the numbers, we'll have the int, I don't know, value to find. We'll have an int for the start index, and we'll have an int for the end index. Does that sound reasonable for values here? So now this one with all of the other information here is not very friendly. I don't want to have to say, hey, find me this value inside of a vector, start at 0 and go to the end. That's not super friendly. So we probably want a non-recursive function, right, that just takes the 2 parameters. So recursive binary search, given the vector of int for the numbers and the int value to find. Right? And then the only thing this is going to do then is going to call the recursive one that has the additional information. That's that helper function. I had a couple of people ask about the midterm question for that one. Yeah.
Why can't we just make that correct the parameter to default? Like you don't include it, just make it 0 and the size of the vector.
So you can't say numbers.size as a default here, right? So that's probably the only reason. We could have a different default value and say, hey, if this other default value, go for it. That could work too, right? So if you want to default this to 0, so instead of like numbers of size, maybe like -1, and then if it's -1, we'll assume it's number size. We can do that. Feels a little bit trickier to have to check for that other thing. I don't know, rather than just having two different functions with an overload. It could totally work. We can do that approach if you want. Do that.
I'm not sure which one's smart.
Efficiently wise, I don't think it matters. It's just now we have to have a check for if it's -1, set it to number size, and that's not a bad thing. Probably ever so slightly slower because you have to check for that now every time. It's still logarithmic, so even if it's like a billion items, by the time you chunk that in 2, you've done it like 8 times. 8 operations is not slow. So, yeah, that's fine. I mean, either way. Oh, anonymous meow. I can't even say your name here. How do we pronounce that? Anna, mouse meow. I don't know. Okay, they did mention it. Yes. Okay, so we're not going too crazy here with our recursive search, right? But the idea, we want to find the middle point, right? So okay, so we could check. Hey, if my end index is equal to -1, then we'll set end index to numbers.size -1, right? Because we want the last actual index, where size is the total number, right? I feel like we should know this by now, but based on the number of errors I've seen here recently looking at people's code, okay, that's all right. So I will remind you over and over and over, there is no index at size. So we're going to find the midpoint then. So the mid then is going to be my end index minus the start index divided by 2, and force your order of operations, right? Otherwise you get start divided by 2, which is no good, right? Make sure we're doing our math correctly here. So mid index or middle index, right? I always harp on people's names. So take the end minus the start, divide by 2. That should tell me the midpoint of wherever that range happens to be, right? Whether or not I'm at the beginning and end or I'm halfway in the middle here, right? It's the average of those two. Now I can check, hey, am I at the middle? If my numbers at the middle index is equal to the value to find, we found it. We're going to return my middle index, because the whole point here is to find the index at which this value is, right? We found it. If it's not there, we're going to check, are we greater than or are we less than? So if my number's at the middle index, how about we say if it's less than the value defined? So that means the value defined is larger than our middle. That means we can throw away the whole first half. We need to recurse. So we're going to return my recursive search here, right? My recursive binary search, given the numbers, given the number defined. Now my start now is going to number value defined. Where do I want to start? Well, I know it's not middle, so I'm going to go middle plus 1, right? And then my end is still the end index, right? End hasn't changed. If it's not greater than, and it's not equal to, so I guess this could be an else, right? Else I'm going to return. Now I want to keep the start index, and I want to end at the middle index -1, right? Because I know it's not the middle, so let's go middle -1. So what we don't have in here is a base case, right? We sort of cheated and did this badly. So how do we know? I guess this is one base case where we found it, right? The other base case is, well, what happens to my start and middle? So let's just imagine for a minute, if I just have, say, 4 values, right? I'm going to get, my last index will be 3, then my start is 0. So 3 minus 0, start minus end, 3 divided by 2, I'll get 1. Okay, so let's put these out like in a notepad here. So we'll throw out 4 numbers here. We'll actually do like a little pretend search. 3, okay. Oh, those are really tiny. We'll just put them in here, I guess. We got a 3, 23, 10. Okay, so 10 should go over here. One more number, and 31. Okay. And what number do we want to find? We want to find a 23. Okay, so we're going to find a 23, right? So we said find the middle point. So 3 minus 0 divided by 2 would be 1. So we're going to look at index 1. Is 23 10? No. 23 is greater than 10. So we're going to take the right half. So our recursive search here, so I guess our first call then on finding 23, start with 0, end was 3. Okay, and we're going to recurse. So our start then will be the middle plus 1. So start is 2, end is 3. Right? End stays the same. So now we're going to add those together. 5 divided by 2 will be 2. Right? So this mid is 1, mid is 2. Right? Okay, let's check for 2. Now it is at 2. We found it. All right, that was easy. What if we're finding 31? When our mid is 2, it's not 23, so let's go plus 1. So now our start will be plus 1. So start is 3, end is still 3, middle becomes 3. Easy. That worked out okay. All right, so that checks out. That checked out. Finding 10 would work. How about if we wanted to find 3? We start at 0, end at 3, mid is 1. We're less than, right? So then we want to go, our start would be 0. Our end would be 1 minus 1 would be 0. Okay, sure. So then middle's 0. We found it. What about a number that we don't have? Right? How do we get the -1 value? Well, if we wanted to find 15, right? All right, well, we're going to start at 0. We're going to end at 3. Our middle point is 1. It's greater than, sure. So then our start will be 2. Our end is still 3. Middle's 2. But now we're less than here. So what happens in our logic? Well, we said, okay, well, if we're less than, we need to keep the start. So start is 2. End is -1 is 2. The middle's 2. Okay, it's not at 2, it's less than. So our logic says, okay, well, keep the start point, take your end -1. So now start is 2, end is now 1. So our base case then should say, hey, if your end is less than the start, we didn't find it, right? Okay, well, what happens if our start gets past the end? The other way around. I guess it's the same thing, right? If start's greater, if we move the other direction. So our base case here, then we can check. We can say, hey, if my end index is greater than the start index, return -1. We didn't find it, right? This is the base case, not found. We don't need to, we could raise an exception if you wanted to have it raise an exception if it's not found, or you can use the -1. Hey, we didn't find an index, depending which convention you want to follow, right? I like the -1. Hey, that indicates we didn't find it. If you want to raise an exception and say not value not found, we could do that too. Totally up to you. Maybe raise exception. Trying to remember what find does. Does the vector find? Doesn't it give us -1? ++ stl find. What does it do for us? It's like a good. Wow. C++ algorithm find. Okay, this is probably better. Okay, if it's not found, it returns last. Okay, sure. All right, but this will probably work for us then, right? Because we're either going to return the middle index or return the -1 for us. So should we make a vector of int for numbers? Let's try it. Like, let's do our 3, 10, 23, 31. 3, 10, 23, and 31. And then let's try and find those numbers then, right? You do that. See what index we get out. So how about for int number in numbers, we can see out my recursive binary search of numbers, and we want to find the number. See what we get. All right, that's not going to be the prettiest output. So maybe we'll say it's searching for the number and then found at index, and then that. Is that any prettier? And then an end line. We don't have enough screen here. I'm sorry. It's too wide. See what we get? So it should get 0, 1, 2, 3. And if we also want to search for something else that's not included, like 15, right? We should get -1 because it's not there, right? Make sure it doesn't crash on us. Test it out, right? See if it works. Is my sugar going low? Uh-oh. That's a bunch of -1s. Something's not right here.
Oh, because set the default parameter set start to 0 and to -1, so it's always less than the check the base.
End index is, it should be less than, right? Less than, not greater than. Yeah, so if we did this before we did this, we would have had a problem. That's good thought, but I think we just were backwards with less than. Let's try that. Oh, crashed. Stack Overflow. All right, well, we're not catching something somewhere, right? If we recursed forever and crashed, yeah, look at that. We recursed infinitely and crashed, so we didn't catch something. What kind of output do we get? Do we see our output window? Okay, so it's on searching for, how pretty that is. They made ASCII art. It's amazing. It's in the standard library. I was searching for 23, so something didn't work with our search for 23. So if we're less than the value defined, middle +1. If we are greater than, keep the end, keep the start. Why did it crash on us? I thought that was going to work. Okay, let's try it in debug mode. See what happens. With a breakpoint. Let's try a breakpoint. So let's put a breakpoint in our function. Where do we want to check? How about maybe here? So when we're trying to find 3, we know that works. We'll just continue. That should be fine. Okay, we're trying to find a 10 worked. No, that was okay. We'll continue. Trying to find a 23. So here's where it fails. Somewhere in where we're trying to find 23. Currently, our start index is 2. Our end index is 3. Okay, so we should be able to find the 23 in our vector, right? Because our numbers vector was 3, 10, 23, 31. So what happens? So we calculate middle. Middle index is now 0. Is that right? End index is 3. Start index is 2. 1 divided by 2, 0. That's not what we wanted. We wanted, So this calculation here is bad. Because this got me 0, but I really wanted start plus that. Right? If I just divide start minus end, I want to take the difference of that plus from the starting location. Because I don't want to go back to 0, right? I want to be from start, how far off should I go? Right? I think I want start plus, or start index plus this arithmetic divided by 2. Is that going to give me where we want to go?
Well, if it's 0, then it just
It's 0. That's okay though, right? Eventually. So like if we're trying to find 23, right? Let's think through it for a second. So we start at 0, we end at 3, midpoint's 1. Because 3 minus 0 divided by 2 is 1. So then 23 is greater than 1. So then our start should now be 2, end is 3. So this is where our math was wrong. So 3 minus 2 is 1. Divided by 2, interdivision is 0. We don't want mid of 0, right? We went the wrong direction. But if we add that to start, we want mid to be 2, because now we have 2 plus 0. I think that's going to work for us here. Let's try it and see if it runs. I guess we can take our breakpoint out and see if it crashes. hey, okay, 0, 1, 2, 3, -1 wasn't found. Seems to be working okay. Now we want to try some other cases though, right? Because there's still other things that could happen, right? How about if we find 0, right, all the way to the left, or find something larger than 31? Make sure it's working for us here. Yeah.
This only works if they're sorted and created at least.
Yes, so this only works on a sorted function. Sorry, we kind of skipped over that briefly at the beginning. So in an unsorted list, we just have to look at all things. If it's a sorted list, now I can do my split the difference, start the middle sort of thing. So that idea of preconditions and postconditions, I think I briefly mentioned that. I think the book talks about it a little bit. iBooks does, maybe. Yeah, does it? No. Okay. Sorry.
When we write our recursive binary search function, should we have the assumption that it's already sorted, or should we check ourselves?
I mean, checking to see if it's sorted is going to take a while. So for us to check that, we'd sort of would lose all the performance benefits. So we kind of just have to assume it's sorted and that it only works. So if you use a binary search on something that's not sorted, you're going to get bad results, and that's just on you. Do we not talk about preconditions and postconditions? I feel like I mentioned it. No? Okay. So a precondition is something that has to be true before it runs, and a postcondition is something that's true after it runs. Precondition, something that is true before it runs, and a postcondition is something that's true after it runs. So these are really common. Some people really love these. I don't. So that's probably why I've never talked about it before. When you get to 350 algorithms analysis or data structures and algorithms analysis, this is really big. And generally the folks who teach that are big on this. I'm not. I've never taught it. So maybe that's why. For certain algorithms, they only work if you meet these preconditions, which I think makes sense. Our binary search only works if you're sorted. So thank you for pointing that out. That's good to be explicit about here, right? If you're not sorted, you're just going to get some weird stuff. It's just not going to work for you. No good. And then that post condition idea is what's true after we run. Well, I'm going to give you the index or -1. I don't. This one is a little bit funnier sometimes. Or like if you go and sort a structure, it'll be in sorted order. So you can have a function to sort here, and there's two sorts we can look at. So we're just doing searching right now. We'll talk about sorting in a minute. Yeah. Well, yeah. So an unsorted search is just start at 0, go to the end. It's not really a good way to optimize any of that because it's not sorted. We can't, start at the end, start at the beginning. We don't have a whole lot of ideas here on how to find something. Yeah. Yeah, the brute force. So let's take a look, see how we're doing here. So our iBooks, this one here, right? Searching and sorting. Our binary search. Look at that, we're doing that one. This O notation, sure. Algorithm analysis, we kind of talked about, time complexity. There's also the space complexity. We don't get too much into that one, but like how much memory are we using? And there are ways we can do things faster if we use more memory, which is really cool. We don't get too much into it here. Selection sort and insertion sort are the common ones. Quick sort and merge sort are a little bit more advanced. We don't get too much into. We'll talk about them here. There's a really cool video, Sound of Sorting, but if I play it, we get copyright strikes because it's another YouTube video, which is fine. That's fair. All sorts of interesting ways you can sort things. But before we go do that here, media, there we go. Let me put some music on. My sugar is going low. I can feel like I'm getting really loopy here. So give me 1 second. We'll go find our shaping the slides. I gotta go get food. say like, yep. We'll be back in just a minute. I'm still trying to figure back up here. I'm halfway through my code. It's starting to get a little better, but we're get up the research page. Right now, like what sort of research is happening. Okay, it's interesting. So this is uh, this is the CIS. Lists some of our folks here. Dr. Baca integrated treatment of ransomware through software of the National Science Foundation. Asking what that Millennium, developing machine vision automated storing of visual models. Grants here, so like this is active funded research happening at the company with the things. This one, autonomous driving from the steering company. Dr. Heaney, he brought in a lot of grants. Oh, I'm sorry, the music. Thank you. Yeah, we're just chatting right now when my sugar's low because I'm feeling really loopy. Looking at current research topics that tenure track faculty are researching. Here, 2 million from U.S. Department of Transportation.
It looks like unrelated research. Or is that right? It's on your recent GE one.
So we tend to have a history of being a little bit more automotive focused here at Dearborn, our campus, for sure. And we have like partnerships is probably the wrong word, but like connections with people doing that sort of thing. And like once you're doing research in this area, it's easier to get grants to keep doing research in that area. So some of these other things are like, I have no idea what this is. Okay, that's about eyes, right? Oculars, eyes. Oh, eye, right there. There's the word eye. I don't know. Models for shape detection from Educational Testing Service. Sure. Detroit area pre-college engineering program for some like small amount here. That's fun. But yeah, all sorts of engineering research here. So the tenure track faculty, the expectation, and I don't know how well this is like, I don't know what the right word is, pushed or enforced or moderated. Like, is they're supposed to bring about half their salary in grants every year in funding every year. So that's the idea. So
does this money go to school or to them?
To their research program. That's all I know. It's definitely not right to them. Definitely not salary, but like to their particular research program. And then part of this funds are like PhD students. So if you get accepted into the PhD program, you get your tuition waived in by doing service, by being like a student teacher, essentially. Sorry, a GSI, or being a research assistant in someone's lab that's funded through the research money, that sort of thing. Like $1,000 a credit hour. Yeah.
How many credit hours?
60 something.
60?
I think so.
Wow.
Yeah, it's not cheap. I mean, your undergrad's not cheap either, but it's more. But so that's the idea now that our PhD program is affiliated with Rackham through the Rackham School of Graduate Studies in Ann Arbor. They have their own rules and regulations around that sort of thing. So part of this funds labs. So some of them have labs full of PhD students who do research and that sort of thing and publications, and it's a whole fun thing.
So you did to waive your PhD?
No, so I was doing a Doctor of Engineering program, but I recently had to drop out of that because I was going to run out of time due to family issues. But so that was going to be like a self-funded part-time thing. So slightly different, and all sorts of other interesting rules. Yeah, all sorts of fun things. How do you communicate with pedestrians? Someone had research. Yeah, oh, I gotta find it. This was a really funny article. Is the audio better now, Crow? Anonymous with guys. Yeah, yeah. Come on. Sometimes this website sucks here. There was a picture of it. Where's the picture? Is it just the video? Okay, we'd have to watch it on YouTube, but like the eyes would be like controlled, and when it saw a pedestrian, like it would like shift the eyes to like make it look like it was looking at the person. But that was like really useful because you can see a driver, the driver can wave at you in a real car or human powered car vehicle. My sugar's low. Feel bad for me. Um, so if the autonomous vehicle can like indicate that it has seen you as a pedestrian, you feel safer crossing the road. And like if the car stops and waits for you to cross the road and you don't know that it stopped waiting for you, and you're like you start and then you stop and you start and you stop and you go, like that would create a traffic jam. So this indication, like the eyes look at you and like I don't know, something like, okay, it's safe to cross. It saw me. Makes a lot of sense. It sounds stupid, but like it makes sense, right?
You meant how long you go. Like if it malfunctions and then the car just stares at you while it mows you down, like that's on the news, So it's pretty traumatizing for anyone. So
Yeah, I mean, human drivers will stare at you too while they mow you down. So I don't know if this is worse with googly eyes.
You with the eye the whole time, That's the car's facing like a motor.
So interesting stuff. All right, feel a little better here, less shaky. Let's talk about sorting. So you're doing a little bit for the project here, where you're putting stuff in sorted order, but you're not taking an unsorted list and sorting it. So there's two main approaches we're going to look at here because they're the easiest to understand: the selection sort and the insertion sort. And they're very similar, but they work kind of opposite. So the idea is we take an unsorted list and we want to sort it. So if we have some numbers here, like our numbers here, let's unsort these. Is that a word? Unsort? Shuffle? Scramble? Something with them. 31 and 23. So if I give you an unsorted list here, we want to sort it here. So let's go and add a little function here. We want to void, we'll call this a selection sort. Given a vector int numbers. So the idea with a selection sort is we're going to select the smallest item, and then we'll select the next smallest item, and select the next smallest item, and select the next smallest item, on and on and on, until we've selected all the items. So we'll look at it, and we'll say, this is the smallest number, right? Because anytime you're given a list of numbers and we say find the smallest, you know the first one's the smallest until you know otherwise. So, okay, 10 must be my smallest number. Let's look at the rest of them and see if I can find something smaller. Okay, 3 is smaller. 3 is now my smallest number. Not smaller, not smaller. Once we find the smallest number, we put it at the beginning. So then we would swap 3 and 10. Say, okay, put the smallest number at index 0. Now we know index 0 is sorted. Where's the next location? Now let's start at index 1. Look at all the items. Find the smallest one. 10, 31, 23. Right, 10. Doesn't have to move at all. That's fine. Now we know these two have been sorted. Now we go to the next index, right? 31. Let's find the smallest number. Swap, sort, swap, sort, swap, sort, swap, sort. That sort of thing. So we're selecting the smallest, but you can imagine this is kind of slow, right? So if we have n items in my list, and I have to look at all n items, and then I look at all n minus 1 items, and I look at all n minus 2 items, and all n minus 3 items, all n minus 4 items, all n minus 5 items, on and on and on. When you add all that together, you get n squared, right? The number of operations, it's n times n minus 1 divided by 2. That sounds right, pretty sure. And that's why you take calculus for fun things like that. Right? It gets an n squared, whatever coefficient we throw away, 0.5n squared, we don't care. So that's slow, but it works, and it's pretty basic. So we can start with our selection sort. So we're going to have the int for the current index is 0. And we're going to say, while my current index is less than my numbers dot size. I'm going to keep on going, right? So we're going to start at 0. We're going to find the smallest item, put it at the current index, increase current index. Start at current index, find the smallest item, put it at current index, move current index. Keep going, keep going, keep going. You could do it with a for loop as well. It probably would work out just the same. Say for current index 0, current index is less than numbers dot size. Current index plus plus, there we go. We'll do that. We'll do a for loop. excuse me. So we'll have the smallest number, then is going to be numbers dot at current index. Because we're going to assume this is the smallest until we know otherwise. Right. Now we need to loop through the next n items. So another loop here for int, I don't know, what do I want to look at? Index to check is going to be my current index plus 1. My index to check is less than my numbers dot size. The at thing row is with our vectors. And then our index to check plus plus. Now we can see, do we have a new smallest? So if my if my numbers dot at the index to check is less than my smallest number, we have a new smallest number. My smallest number is equal to my numbers dot at the index to check. And actually, what we really need is the index here. That's what we really want to keep. Because we have to do the swapping, we don't really care what the value is. So it's probably easier to just keep the index here. So we'll say the smallest index then is going to be the current index. So if my numbers at is less than my numbers at the smallest index here, then we'll take the smallest index, set it at the index to check. So if we just deal with indexes, it makes the swapping easier at the end.
Why do we need the smallest index?
Because the smallest index could change. Because I'm going to eventually take the smallest index, so it might be like 7, and put it at current. I'm going to swap it with current.
Yeah, but once you do that at the end of the for loops, and then regardless of that, it's still be reset.
Oh, I'm going to put it at current index, but I need to know where the smallest number is. So like when 3 was over here, so this would be current index is 21, and my smallest index is going to start here. It'll become 10, then it'll become 2. This index here would be 2. So current index is here, smallest index is here, so I can swap those. So I need to keep them separate, so I can do that swapping at the end. Yep. Got another. Yep. All right, so now I can find the smallest index. So I've now gone from the current plus 1 all the way to the end to find the number at the index of the smallest number. Yeah, Crow, it's almost the same thing, but you get bounds checking with vectors with the at notation. The square brace notation, you don't get the bounds checking. So if you read an invalid memory address, it doesn't crash on you. So at's safer. Now we're going to swap. All right, so we'll take my int for temp is going to be my numbers at the current index, and then my numbers at the current index. We can assign my numbers at the smallest index, and then we can take my numbers at the smallest index and assign it temp. Oh, nice. In the standard? Okay. Nice. Yeah, I mean 3 lines versus 1. Yeah, I guess saving some lines of code is good. Do you want to use that swap instead? We can do it either way. I already have this written, so that's okay. Right. But that's all this loop does. That's it. We go start at 0, go to the end. We could actually stop at 1 less than size, right? Because like that last one, nothing's going to happen, but that's okay. Once we've picked out all the other numbers, we've swapped all the other smallest ones in, we know the biggest is at the end. So like you could save one operation, but we don't care too much. And like this loop won't run at all anyway because we start at +1. So like we'd swap with ourselves at the end here, but that's okay. So we should be able to sort then. So let's give it a vector that's unsorted here. So let's try, I'll just use this one again, right? Because we should be able to take an unsorted vector, sort it, and then do our binary searching on it, right? So let's put this out of order. So like 23 and 31 and 3. How's that? And then we'll call our sort, our selection sort, given the numbers vector. It should turn it into a sorted order, and then we should be able to go and search, binary search it. Oh, uh-oh, Stack Overflow. Recursive binary search failed. It worked before. Maybe our sort was bad. All right. We'll see what our sort's doing then. All right, so we're going to sort our vectors here. So here's our numbers list: 23, 10, 31, and 3. So the smallest index starts at 0. We're going to go check all of our values here. We get a smallest index, smallest index, smallest index is now 3, which should make sense, right? Because we wanted 3 was the smallest. So we should be swapping the 3 and the 23. Okay, that's 3 and 23 swap. Then we have 3 and 23 swapped. We'll go check the next one. Current index is now 1. Smallest index is 1. Check for the next smallest item here. It should still be 1, right? Nothing should change here because it's still 10. So 10 and 10, nothing should change. Okay, now we're going to go check the next one here at 31, index of 2. So that one should change with index 3. Yep, we have a new smallest. Loop's done. We swapped 23 and 31. Now 31 swaps with itself, right? Nothing happens. Selection sort's done. Oh,
It's not returning, it's not reference.
yeah, we didn't, we passed a copy. So can we pass the reference, the numbers? Nope, that was wrong.
I think you have to put that in.
In the, yeah, if we take a reference here, numbers, is that gonna do it for us? There we go. So if we ask for, which drives me nuts, because like, how would I know if the function wanted a reference or not, if I didn't give it a reference or not? But okay, sure, that's okay. So we give it a reference, and now our changes stick. So we didn't have a copy. Yep. And then we don't crash. That's funny. Our binary search just crashes if we were out of order. Why would it not have ended? Oh, because the less than and greater thans, probably. It probably went back and forth, back and forth, back and forth. That's probably what it was. Okay, cool. That's a selection sort. So even if we're in a sorted order already, a selection sort will still take O of n squared. It still has to check n items, and n minus 1 items, n minus 2 items, n minus 3 items, n minus 4 items. The insertion sort is ever so slightly different, and it has a better best possible time. So like selection sort, the best possible time is still n squared, no matter what. With the insertion sort, the best possible time is just O of n, which is cool. So if you're already sorted, it can just really quickly go through. Nothing has to change, which is nice. So our insertion sort, given a vector of int numbers, and again, this doesn't have to be done with vectors of integers. So we're using ints because it's really easy here, but we could use a template type. And as long as you can compare less thans and greater thans, they will work with any type, right? That's the whole reason why we like templates. And that's why the standard template library works for these sorts of things. There's a sort function in the standard template library we can sort with. You don't have to write your own. And it worked really fast. But we spend some time looking at them so we understand performance, and they're easy ways to look at why things are slow, why things are fast, that sort of thing. So we know they're not great. You would never expect you to write your own, but we spend some time talking about them anyway, because that's what we do. Sure. Right, so on an insertion sort, what we're going to do is we're going to insert items into the sorted portion of the list. So we will start at the first item and assume this is my sorted portion. So if we look at my list here, we'll say, okay, 21 is sorted. These 3 are not sorted. And then what it does is it will insert the next item into the sorted portion where it belongs by just moving it back 1. And moving it back 1, moving it back 1. So it'll start swapping. So it gets to the 10 and says, okay, are you less than the thing before you? Because we know everything from 21 back is sorted. Well, it's only one item, but that's fine. So it says, yes, you're less than, so swap. So now we have 10 and 21. And we said, okay, if you're at the beginning, you're done. Or if the thing before you is less than you, you're done. Sure, we're done. So we've swapped. Now we get to 21. I'm sorry, so now we know 2 items have been sorted. So our sorted portion is growing as we go. Now we look at 3. We'll say, okay, are you less than the thing before you? Yes. So then we swap. So now we get 21 and 3. Are you less than the thing before you? Yep, swap. So then 3 and 10. And now we got to the beginning, we know we're done. So now we have 3 items in sorted order. We get to the last item here. We say, are you less than the item before you? No. So we're done. You don't have to change it all. So you can see if you're in sorted order, it just takes n checks. It says, okay, are you less than the thing before you? No. Are you less than the thing before you? No. Are you less than the thing before you? No. So it will just be n checks along the way. No additional work has to happen with an insertion sort. So we're going to say for int the current index. So we're going to start at 1 with this one here, and we'll say our current index is less than my numbers.size, and then my current index plus plus. So starting at 1, because we know the first item is already sorted, we know we're great. So now we're going to start checking. As long as we are less than the thing before us, we want to keep on going. So I think this is usually probably easier as a while loop. You can do it as a for loop, and then like you've got multiple conditions in the check here, and that gets a little funny for for loops. You can do it, but it's kind of bad form. So we can say while my here my item. We need one more index. This is the current index. We need int previous index. Now, what do we want? Index to check. Index to check. Is my current index -1? So my numbers at the current index is less than my numbers at the index to check. So as long as we're less than, right, we want to keep on swapping. I guess we don't even want current, do we? We need, we want to keep swapping one at a time. Shoot. I'm going to use, I will just start here. We'll do -1. So we can change index to check. So if we are less than the thing before us, right, and our current index then, and our index to check, index to check is greater than or equal to 1. Because if index to check gets to 0, right, we can't take 0 minus 1. We're no good here. So we're going to say, okay, as long as we're at 1 or more with our index to check, and we're less than, we're going to keep on going back. So we can keep swapping our way back. So we can swap. Should we look up that swap? Swap. Let's see. Just swap A and B. I'm sorry? Is it really? Oh my goodness. All right, I'm sorry. I was just going to keep talking. Thank you. All right. Well, we can come back. We'll finish this up on Wednesday then, and then we'll talk more about. Oh, we have all Wednesday too. Okay. Yeah, we're good then. Sorry. We'll finish this up Wednesday. Thank you for shouting at me. Folks, take care.